So up till now we tried to understand the concept of Bode plot, and we saw how to draw the Bode plot of a general first order and second order system. Today we first of all will summarize the things that we learned in the previous two lectures, and then we will move on towards talking about the procedure, step-by-step method to draw Bode plots, and we'll try to solve a problem in hand. So Bode plots contain two separate plots. One is called as magnitude, the other is called as phase plot. And magnitude plot, the magnitude of Gg omega is expressed in decibels, that is 20 log to the base 10 of magnitude Gg omega is drawn versus omega on log scale. While in phase plot, the phi, which is angle of Gg omega expressed in degrees, is drawn versus omega on log scales. So by log scale we mean the scale that we usually see in a semi-log paper. So omega is normally taken along the logarithmic scale. So that is what we refer log scale. So this is the log scale on x-axis. And the unit of this log scale is normally in Bode plot termed as decade. So as I told you before, that decade is the ratio between the two frequencies. So if we say that this is omega 2 and this is omega 1, then omega 2 divided by omega 1 should be 10. So we have, starting from this particular point, 1 decade here, then 2 decade here, and 3 here, and so on. Likewise, we have, while we draw magnitude plot, we have decibel on y-axis. So this one is a linear scale, 10, 20, 30, 40, 50, 60, and so on. If we draw a phase plot, in that case, we are going to take negative y-axis starting from 0 degrees, then we move on towards negative angle minus 90 and minus 180 degrees, because we normally see phase plots to be negative. And we also talked about the slope of the curves that are drawn on Bode magnitude plot. So suppose that this is the vertical axis has marking with a difference of 10, for example 10, 20, 30, 40, and we are interested in drawing minus 10 dB per decade. So we'll be drawing a line having a slope minus 10 dB per decade in such a manner that it will be crossing the point at 10 on vertical axis and 1 on the x-axis. So this line has a slope of minus 10 dB per decade. Likewise, we can draw minus 20 dB per decade, minus 30 dB per decade, minus 40 dB per decade, minus 50, minus 60. Then we can draw positive slopes as well. For example, if we are interested in drawing 20 dB per decade, a positive slope, then we'll be having a line like this, and 40 dB per decade, 60 dB per decade. So drawing a line with certain slope is very similar to what we have learned while we drew line that has general representation of y equal to mx plus c. Now if this particular line represents a slope of minus 20 dB per decade, then all the lines that are drawn parallel to this particular line anywhere on the graph paper on semi-log paper will be having slope of minus 20 dB per decade. So all these lines have slope of minus 20 dB per decade. Likewise, any line drawn parallel to a slope of minus 40 dB per decade will have slope minus 40 dB per decade. So these are something that you already know about, and it's not very important to discuss, but just for a quick review of how to deal with plots on semi-log paper, it's important to discuss slopes on the semi-log paper as well. Now we discuss the procedure or the rules or the steps that are involved to draw a Bode plot. And till now we were trying to generalize, or we were trying to conclude the concept of a Bode plot, and we were making certain assumptions when we didn't knew about the values of omega n and zeta. So we represented the first order and second order system in general form, And from that general form of the system, we try to obtain the Bode plot taking certain assumptions. But now we'll discuss the procedure that are required, or the steps that are required to draw Bode plot. And I will try to solve a problem which will be having the values, the transfer function with its values specified. So the first procedure is to obtain the transfer function in time constant form, and this has already been discussed in unit 3. So this type of representation is the time constant form, where you have terms like 1 plus st, so 1 plus sta into 1 plus stb, or 1 plus st1 into 1 plus st2. So these are all time constant forms. Now we replace, the second step says to replace s in the transfer function by j omega to obtain the frequency response function. So this is the same rule that we had been discussing in unit 4. So whenever we try to obtain, we try to perform frequency domain analysis of any system, the rule 1 says to convert the transfer function such that all the s of that function are replaced by j omega. So we obtain frequency response function. Third rule says to obtain the corner frequencies from the expressions of type 1 plus j omega t. So after you replace s by j omega, you will be obtaining g j omega and all the terms replaced, s replaced by j omega. So we'll be having here 1 plus j omega ta, 1 plus j omega tb, 1 plus j omega tn, 1 plus, you will be having j omega to the power n, 1 plus j omega t1, 1 plus j omega t2, 1 plus j omega tm. So these are the expressions of type 1 plus j omega t. Now in order to obtain the corner frequencies, and as I told you before, that corner frequencies are the frequencies where the curve will be taking the turn. So in magnitude plot, you'll be having a straight line, then a turn again, then you might have more turns depending upon how complex the transfer function is. So we'll discuss again about this in the problem that is upcoming. So corner frequencies are obtained from this expression by taking the reciprocal, like omega c equal to 1 upon t. So for example, if you want to obtain corner frequency corresponding to 1 plus sta, then in that case you will be having omega c equal to 1 upon ta. Likewise, corner frequency corresponding to this term will be omega c equal to 1 upon tb, and so on. Then we obtain the expression of gain in decibels, which is 20 log to the base 10 magnitude of gj omega. So we'll first compute the magnitude of gj omega, then we'll be taking the log of it with 20 multiplied. So this is the decibel value of the magnitude, and we call this as nu. Then we obtain the expression of phi, that is angle of gj omega. So this is again that we already know about, and when we discussed about phasors, so we learned to obtain the angles as well. So this becomes the phase of the Bode plot. So we'll be having two plots, the magnitude versus omega and phase versus omega. And since Bode plots drawn by hand are approximate plots, we approximate expressions of dB for multiple different ranges of omega. So we saw this in our previous lectures, that we had different values of different ranges of omega, and we were trying to approximate the plots. And again I repeat this, that Bode plots that are drawn by hand are approximate plots, not actual one. So you in fact draw the asymptotes to the actual curve when you draw Bode plots by hand. So whatever we draw by hand, the Bode plots, so they are nothing but the asymptotes to the actual curve, or the exact curve that we used to draw by softwares. So if you try to merge the curves you obtained by hand and the curve that you draw by software, you will clearly observe that the plots that are drawn by hand are the asymptotes to the exact or the actual curve drawn by software. So we approximate expressions of decibels for multiple different ranges of omega depending on the number of corner frequencies. So as I told you, that corner frequencies are the frequencies or the points where the curves will be taking turn. The curves will be taking turn. And the times of approximation will depend upon the number of corner frequencies encountered into the system. So we'll see this in the upcoming slide. And this was also discussed in our previous lectures and will also be discussed again. So here's a simple problem, and we are required to draw the Bode plot of this system. We have a transfer function of a system. The system is represented by Gs, which is 10 into s plus 10 divided by s into s plus 2 into s plus 5. Now we start with the first step, which says that obtain the function, the transfer function in time constant form. So what we do is we divide this expression by 10. You divide these expressions, this one by 2, this one by 5, and equally multiply them by the same term. So 10 by 10 here, 2 by 2, 5 by 5. So what we get is this reduced form of expression. So 10 divided by 2 into 5, again 10. So you have a time constant representation of the system. The second rule says to replace s by j omega. So we are going to substitute s equal to j omega in this expression to obtain the frequency function j omega, so which looks something like this. And then we identify the corner frequencies. So as I told you that corner frequencies are obtained by the expressions of type 1 plus st. So if you look into this expression, you have 1 plus 0.1. In fact, it's not s, it's j omega now, because we have replaced s by j omega. So 1 plus 0.1 j omega, and this will be contributing one frequency. Then we have second frequency from 1 plus 0.5 j omega, then third frequency from 1 plus 0.2 j omega, like this. So from we learned that corner frequencies are obtained by 1 upon Tn. So the corner frequency we obtain from this expression is 1 upon 0.1, which is 10 radians per second. From this expression we obtain 1 upon 0.5, which is 2 radians per second. From this expression we obtain a corner frequency as 1 upon 0.2, which is 5 radians per second. Now the second thing, while we obtained all the corner frequencies, is to identify which of them is smaller and which is large. So we see that 2 is the smaller frequency, then 5, then followed by 10. So this is the smallest corner frequency, then followed by this 5 radians per second, and after this comes the frequency 10 radians per second. Because corner frequencies are the frequencies where the Bode magnitude plot will be taking turn. So we'll have to mark these frequencies on the semi-log paper on the x-axis. Now before marking this on the x-axis, we'll first assign the abbreviations, which of them is first. So since 2 comes before 5, we'll be assigning this as 1, and then this will be, because 5 is smaller than 10, so after 2, 5, there is a frequency 5, then you'll be assigning 2 here, and then you'll assign 3 here. So this becomes the first corner frequency, this becomes the second corner frequency, and this is the third corner frequency. And we'll mark these corner frequencies on the semi-log papers. And one more thing, that while you are going to draw the Bode plots, now there is an option that all depends upon you, that at what frequency are you going to start on x-axis. So this first of all depends upon the corner frequency, the smallest corner frequency you identified. So since you identified a smallest corner frequency 2, it means that the starting point on x-axis should be less than 2. So it could be 1, because the difference is in decades, which means that you have a frequency multiple of 10. So if you multiply 0.1 by 10, you get 1, then 10, then 100. So these are the difference in decade. So this is 1 decade. This is from here to here is 2 decade. So this corresponds to 0.1 omega. This is 1 radians per second, 10 radians per second, 100 radians per second. And the gap between them is decade. So we are going to select a point on x-axis, the first point, which should be less than the smallest corner frequency. So we can select 0.1 followed by 1, or we have an option to select starting from 1. It's because 1 is smaller than 2 and 0.1 is also smaller than 2. But we prefer drawing from 0.1 because of the reason that we are going to have the turns corresponding to the corner frequency, and if we choose starting from 1, then we'll be having 2 somewhere here, and we'll see that a small part of curve will be seen on the Bode plot, while if you choose starting from 0.1, you'll see a large part of curve starting on Bode plot. So you'll see this when we draw the Bode magnitude plot in the upcoming slides. So now, after identifying on the x-axis the starting point of omega as 0.1, we mark the first corner frequency. So we are going to have the frequency 2 here. So if you're able to see, you can refer to the previous lectures. We had marking here on the top side. If you buy semi-log paper from shop, you will see the marking on the bottom axis. So we have here as 1, then we have 2, 3, 4, 5, 6, 7, 8, 9, 10. Then again you have this. If you mark this as 10, this becomes 20, 30, 40, 50. But since we have marked the initial point as 0.1, so this becomes 0.1, this becomes 0.2, 0.3, 0.4, 0.5, 0.6 up till 1. Then we have 2, 3, 4, 5, 6 up till 10. Then we have 20, 30, 40, 50 up till 100, and so on. So we have a marking of 2 here. So this becomes the first corner frequency omega c1. We mark this as omega c1. Then we have 5 at this particular point because the second corner frequency is 5. We're going to mark this 5 here. So we have omega c2 marked at 5 here. Then we have 10. So this becomes omega c3. So after marking the corner frequencies, these are the points where the curves will be taking turn. Now we go to the next step, which says to obtain the magnitude in terms of dB. So before that, you'll have to obtain the magnitude of G omega as follows. So referring to the expression of G omega in the previous slide, we have this expression. So from this expression, we see that the magnitude, this becomes 10 plus J0. So the magnitude becomes 10. The magnitude of this term becomes under root 1 square plus 0.1 omega square. Likewise, you have 0 plus J omega. The magnitude becomes omega. For this, we have magnitude 1 under root 1 square plus 0.5 omega square, and for this we have under root 1 square plus 0.2 omega square, like this. So 0.1 square becomes 0.01, 0.5 square becomes 0.25, 0.2 square becomes 0.04, and we are left with omega squares associated with that. So this becomes the magnitude of G omega. Then we will be obtaining decibel, dB. dB is equal to 20 log to the base 10 magnitude of G omega. So replacing G omega by the terms that we obtain. So it's written here. Now simplifying this, we get, since this is log, all the terms in the numerator which are multiplied will be added when we separate them out, and all the terms in the denominator will be subtracted. So 20 log to the base 10 of 10. So we have a 10 here, then this term 20 plus 20 log to the base 10, this term. Then we have omega 20 minus 20 log to the base 10 omega, because this is in denominator, then minus 20 log to the base 10 under root 1 plus 0.25 omega square, then again minus because we have terms in the denominator, 20 log to the base 10 under root 1 plus 0.04 omega square. Now we obtain the decibel, a simplified representation, but we are going to rearrange the order in such a manner that the terms that correspond to the corner frequencies, the smaller corner frequencies, arrive first. So we simply rearrange them. So we have this term that will always be there in the expression. The first corner frequency was corresponding to 1 plus 0.5 omega, while the second corner frequency corresponds to 1 plus 0.2 omega, and the third corner frequency comes from 1 plus 0.1 omega. And we have rearranged it in such a manner that we get the first corner frequencies, the term corresponding to the first corner frequency appearing first, followed by the second corner frequency term, followed by third corner frequency term. We do this just to simplify the upcoming steps, because if you look, as I told you before, that we are going to do certain approximations in Bode plot, and the approximations are, we are going to assume different multiple ranges of omega. and how we are going to deal the terms of decibel for these different ranges of omega. For example, if we are going to have omega much less than the first corner frequency. So if you look into these ranges of omega, they come from the corner frequencies. 2 was the corner frequency, 5 was the corner frequency, 10 was the corner frequency. So if you're going to take values of omega much less than 2, and why are we doing this? For this, you'll have to again refer to the previous lectures on Bode plot. As I told you before, that we are going to do some sort of assumptions, and that is why we are going to choose the value of omega much less than 2. So if you choose value of omega much less than 2, in that case, you're going to have these expressions. 1 plus 0.25 omega square, 1 plus 0.04 omega square, 1 plus 0.01 omega square, all 0, approximate 0. Because omega, in fact, this will not be 0. So a slight correction here. The log of these will be 0. So if you're going to take, because if 1.1 plus 0.25 omega square, if you're going to substitute omega much less than 2, in that case 0.25 multiplied by omega square will be negligible compared to 1. Likewise in this case also. So in the square root, you're left with 1. So this becomes 10 to the base log to the base 10 under root 1. Likewise this becomes log to the base 10 under root 1, and so on. So log to the base 10 of 1 is 0. So after taking logarithmic log of the remaining term, which is 1, you get these terms as 0. So this becomes 0, this becomes 0, and this becomes 0 for omega much less than 2. Likewise for omega lying between 2 and 5. So again, this is a very rough assumption, because now we are not talking about omega which is very far from 5 or 2. So this is a very rough approximation, and you actually do not get, this is the reason that you are not going to get the actual or exact curve, rather approximated curves. So when you take omega lying between 2 and 5, the approximation is that these two terms, because 0.04 omega square, if you're going to substitute, let's say a value 3 square is 9. 9 multiplied by 0.04 will be something which we assume to be negligible in terms of 1, and thus this is equal to 1, not 0. Log of these values will be approximated as 0. Likewise, if omega lies between 5 and 10, in that case we are going to have this expression 0. So we are going to have 1 plus 0.01 omega square close to 1, and log of this will be 0. And then if we are going, so what we did is, when we assumed omega much less than 2, so these three terms were eliminated. While omega was lying between 2 and 5, these two terms were eliminated. While omega lies between 5 and 10, this last term is eliminated. While if we assume omega greater than 10, then all the terms will reappear. So we'll be having the full expression of decibel. Now we'll be plotting corresponding to each of these multiple different ranges of omega. So for omega much less than 2, we were left with only the expression this, and all the terms were eliminated. So we'll look into the plot of this particular expression. Then for omega lying between 2 and 5, we were left with the expression this one, and we look into the plot, how the plot for this particular term looks like, and so on. So rewriting the expression of decibel in green, and the assumptions are rewritten again. So let me correct them all. Again, the log of these values should be 1, should be 0. Now if we take omega much less than 2, I told you that we are left with the expression 20 log to the base 10, 10. So this becomes 1 minus 20 log to the base 10 omega. So this is the expression we are left with. And if you look into this, so this becomes 1. So we are having dB equal to 1 minus 20 log to the base 10 omega. So this is very similar to y equal to, this becomes mx minus mx plus c. So c is 1 and m is minus 20. Since log to, now you will have to you'll try to understand that this in fact is, if you correlate this with the relation y equal to mx plus c. So this is x. Log to the base 10 omega is x, not omega. So we are not saying that omega is equivalent to x, rather log to the base 10 omega is x. The reason is that we are saying log to the base 10 omega as x because we are going to plot on x-axis, not linear scale. Had this x-axis been linear scale, in that case we would have referred this as x. Only omega would have been referred as x. But since we are not plotting this on linear axis, rather logarithmic axis, because the x-axis is what? It's log to the base 10 omega. This is x-axis. And that is why we say that the log to the base 10 omega is x and not omega x. So if you try to plot this, you have a slope for this line is minus 20 dB per decade. And for the second assumption, when omega was lying between 2 and 5, we have a slope of minus 40 dB per decade. It's written here. So slope for first case is minus 20 dB per decade, for second is minus 40 dB per decade. And when we have the third assumption, the fourth expression which was eliminated in the previous step reappears, and you have slope as minus 60 dB per decade. So let me explain this also. So because this is minus 20 log x mx, so you have minus 20x, then you have minus 20x again, and in fact this is log terms. So if you try to combine these expressions, so, and in fact if you try to consider this particular, what is the slope of this expression, this term. So since you have under the square root term of omega square, the effect of under root a term written in terms of omega square will be omega. I mean to say that this term root of omega square will have the same effect as that of omega while you plot, which means that the slope of this line is minus 20 dB per decade. Likewise, you have minus 20 dB per decade here. So since you're talking about log values, and the slope will be added, or in other terms you can understand this as minus 20 log to the base omega can be written minus 20 log to the base 10 omega multiplied by under root 1 plus 0.25 omega square. So you have, since you have log terms, so you can multiply this term with this. And I told you that this particular term has effect of omega. So this is similar to multiplying omega by omega, so which gets omega square. And minus 20 log omega square will have the effect of minus 40 log omega. And as I told you that you are going to make this as log omega for plotting on semi-log paper and not log omega square, because the x-axis is log of omega and not log omega square. I guess this makes clear. If you have still problem, you can post me or ask me questions. So likewise, you will be having minus 20 dB per decade. Again, from this you have a slope of contributing minus 20 dB per decade, a slope again minus 20 dB per decade, minus 20, minus 20, minus 20 makes minus 60 dB per decade. And again, you have minus 20 dB per decade here. and minus 20, minus 20, minus, and yeah, of course. So this is important. Again, now you have a slope of plus 20 dB per decade. So you have minus 20, minus 20, minus 20, plus 20. So that makes minus 40 dB per decade. And the slopes are drawn. So this is minus 20 dB per decade, this is minus 40 dB per decade, this is minus 60 dB per decade. Now, after identifying the slope of each of these expressions, you will have to at least identify one point where the curve will pass. So if you identify any one point where the curve will be passing, then that will be enough to plot the Bode plot, because you know the slopes and you know the points where the curve will be taking turn. So if you look into this expression, if I'm going to substitute omega 10 here, so this becomes 20 log to the base 10, 10 minus 20 log to the base 10, 10, which makes decibel dB 0, which means that this particular line will pass through 0 dB when omega is 10. So at this point, the line will be passing through x-axis, will be having a slope minus 20 dB per decade, which means that I am going to draw for this first expression a line that passes through 10 parallel to this line, no matter where it cuts. So it will be reaching in fact 40, because if you draw from 10 parallel to this line, this eventually will meet this particular gain 40. So let's try to draw this, and this is the expression for omega less than 2. If you're going to substitute 10, then dB is 0. So here is the line. So we draw a straight line having slope minus 20 dB per decade and will meet the x-axis at omega 10. But we are going to extend this line only till the first corner frequency is encountered, because after the first corner frequency the curve will be taking turn. And when we say that omega lies between 2 and 5, the slope was minus 40 dB per decade. So the point where the curve extends till omega C1, the first corner frequency, we'll be using the same point and drawing a line with a slope of minus 40 dB per decade till the second corner frequency is encountered. And from this particular point, we'll be drawing a line with a slope of minus 60 dB per decade. And then finally, after the third corner frequency, we'll be again drawing a line with a slope of minus 40 dB per decade. So this is what we obtained in our previous slide. We have slope minus 20 first, then minus 40, then followed by minus 60, then followed by minus 40. And after identifying the first line, we simply drew the slopes. We knew the point that this line will be intersecting the first corner frequency line, the dash line, and after that we drew. So this is how the Bode magnitude plot is drawn. And phase plot, as I told you, is quite similar. It's quite simpler than drawing the Bode magnitude plot. So what you're going to do is you're going to identify GJ omega, and from this you will be plotting phi. You will be opting phi, which is angle GJ omega, by the method that you learn in phasors. So you have tan inverse of 0.1 j omega upon 1, sorry, omega upon 1. Then you have minus 90 from j omega, and you have 0 degree from 10. So this can be written as 10 plus j omega. This can be written as 0 plus j omega. So this will be contributing minus 90. Minus because this particular expression is in denominator. And this is again is in denominator. You have minus tan inverse of point. Sorry, slide correction here. This is 0.5 omega. And this is 0.2 omega. Likewise, this is 0.2 and this is 0.5. So if I am going to substitute different values of omega in obtaining phi, so for example, if I substitute omega as 0.1, what we get is phi is minus 93. If I substitute omega as 0.5, so this can be simply easily done by using your scientific calculators. You get angle this, and these are the angles. I can easily mark this on. And remember that in case of phase plot, you are going to take negative angles, and that is why they will be drawn below the x-axis. And for the first omega, take it. And one thing more, you will always have to coincide the values of omega on x-axis on both the plots. So if you're going to take this as 0.1, you are bound to take this as 0.1. Had you taken this as 1, you will be taking this value as 1 as well. So this is important. Otherwise, you might get a wrong plot. So all the range, all the values of omega taken in the Bode magnitude plot will be same that are taken on the phase plot. So after obtaining these values, so for omega 0.1, I have angle minus 93. So 0 0.1, we have angle minus 93 somewhere here, close to minus 90 degree. Then for 0.5, I have angle minus 107 degree. So I identified 0.5 as a point here. So 0.5, I have an angle of minus 107, which is somewhere here. Then at 1, so this is 1, I have an angle of minus 122 degrees. So my 122 degrees lies somewhere at this point. Then at omega equal to 2, so omega 2 is here. This is omega 2. So at omega 2, I have minus 145 degree. The point lies somewhere here. Then omega 5, this is the point omega 5. I have minus 176 degree, which is somewhere here. So and so on. So you can take further values as well, 10, 100, 1000, and so on, depending upon how many, how much you have on left on the right side. So now you will be drawing this free-handed, connecting all the points that you identified on the phase plot. So this is the required phase plot, Bode phase plot, and this gives you the final Bode diagram. So these two plots are collectively called as Bode plots. And that's all. If you have any questions, you can ask me or post me on Google Classroom, or you can mail me on my email ID.